Okay, great. Good afternoon, everyone. Thank you for joining us today for a new Lunch and Learn, and thank you to Shounak for offering to host for us today. So before I hand over, I just want to remind people that we will be recording the session, so please do keep your camera off if you're not happy with being recorded, and also please use the chat for any questions you might have, and we can get to those at the end. So yeah, I'll hand over to you now, Shounak.
Thanks, Molly. So thanks for inviting me for this session. So myself, Shounak, and I am an assistant professor at the Department of Computer Science, Durham University in UK. So today's topic is on thermal layer computing with the emerging devices. So my primary area of research is in computer architecture and compilers, and where specific objective of my research is to improve the thermal and energy efficiency of the underlying circuitry or underlying devices. So here is the outline of the presentation. I'll give you a brief introduction of my current research activities at the beginning. So where I'll be covering mostly two different avenues. So first one is the non-volatile memories, where mostly I'll be talking about the I'll be talking about the non-volatile memories like STT-RAM or magnetic RAM, or resistive RAM or memory star, and followed by that, I'll also give you a brief about the 3D field effect transistors like FinFET, GAFET, and so on. Then I'll be giving you a very brief description of the TIMO, which is one of our recent contributions published last year in IPDPS conference in 2024. And next, I'll be giving a very brief about our recently developed simulator, which got accepted a couple of months back in IEEE TCAD. The name of the simulator is Hot ReDAM. And followed by that, one of my PhD students work on the FinFET-based multi-core in the domain of real-time task scheduling, which is TreeFET, got published last year in SEM Text. Before conclusion, so I'll be giving all these briefs of these about these three different papers. So on the left-hand side of this particular slide, you can see there is a diagram of a modern CMP. CMP stands for chip multiprocessor, and this chip multiprocessor is basically from Intel family. And this contains actually 4 different processor cores along with multi-levels of caches. Especially here, we have actually specifically it's 3 levels of caches here, where first couple of levels are basically local or private caches attached to the core itself. And if I just take a close look at this particular diagram, you can see this shared L3 cache, which is LLC or last level cache in this chip, is actually occupying the one of the most significant areas on this wafer real estate. And if you are specifically build them in MOSFET-based circuitry, so you can see that their leakage power is super high, which is even more than 97%. And in this entire power consumption is nothing but the wastage of your power. Okay, so this was basically the primary design concerns in the era of MOSFET, so around 5-10 years back. And then if you just take a look at the processor cores, you can see that the cores are usually accounted for generating hotspots, that is their effective temperature or the runtime temperature is quite high, and which was really another design concerns for the architects and the designers over the decades. To address this problem, so researchers have found out a couple of solutions. So first of all is actually about the device. So they are going to change the device or explore more different kind of devices, and one of them is the 3D FETs, that is FinFET, GAFET, and beyond. So this kind of 3D FETs or these confined geometrical shaped devices are really cool enough to handle this situation because their leakage power is really low. On the other end of the spectrum, non-volatile memories or NVMs like magnetic RAM or MRAM or resistive RAM or ReRAM are really one of the really other promising candidates who can actually replace these MOSFET-based CMPs by implementing the memory cells in while designing the caches. Okay, because these non-volatile memories also have very lower amount of leakage. Let's take a look at the upsides and downsides of both of these technologies. So if you just take a look at the 3D FETs like FinFET or GAFET, they have come up with a very good solution over the MOSFET. Their circuit delay is quite low while you are comparing them with the traditional MOSFET designs. And they have also come up with a special kind of characteristics, which is really good. It's called as TEI or temperature effect inversion. This says at high temperature, these devices circuit delay basically drops, and which is really good for improving performance. So more temperature, so more faster your processor or your cache memory will be, which is really commendable. But at the same time, high temperature is not good for the circuit health because of the presence of She. So She stands for self-heating effect. So these 3D FETs have some confined geometrical shape where the conductive filament or the channel is basically encapsulated by some thermal insulator that clogs the heat dissipation, which is really detrimental for the circuit health and can damage the circuitry permanently. So self-heating effect is bad. So while you have the TEI in hand, which is really good, so high temperature is good as well as bad. So you need to find out a sweet spot. On the other hand, you can have the non-volatile memories, which have come up with some good properties like low leakage. They have the upside of area efficiency or higher cell density. That is, at the same area, you can now have more capacity of the caches, which is really good to accumulate more live data on chip. Additionally, they can also be compatible enough with the conventional MOSFET based design, which is really good for their integration in the while you're basically fabricating the chip. On the right hand side, the red color box is basically the downside, which is actually the write cost, nothing else. Okay, write cost for these non-volatile memories are super high while you're comparing them with the MOSFET-based CMPs. Their write energy and write latencies are really very higher than the conventional MOSFET caches. So based upon these two different avenues, so let's take a look at the 3D FET. So my current activities lies upon towards exploring the what should be the sweet spot for different technology nodes for these 3D FETs, while considering several novel core-based as well as cache-based techniques. And on the other hand, for the non-volatile memories, I mostly explore the multi-retention caches, where we usually manage the write variation. So retention is a very new term in this particular presentation. So retention is actually says the entire term is basically the retention time. So this is the time span for which your data will not be corrupted, or it will maintain the correctness or remain unchanged while you are storing them on some non-volatile devices. So once that retention time expires, there is a high chance that your data will not be intact as it was earlier. And that this retention time has a very good relationship with the temperature. Higher the temperature, your retention time will drop. So at high temperature, your data will basically be corrupted very soon. Okay, so you need to actually maintain a low thermal profile to maintain the correctness of, especially the functional correctness of the underlying circuitry. In both the slides, you can in both the boxes, you can see I have written about the compilers. So why compilers? Let's take a look at this particular table. So I have given I'm giving you a kind of comparison between the compilers and hardware. Suppose we have written a code and which we are going to execute. But during compilation, compiler has the liberty to take a look at the entire code, starting from the first instruction all the way to the last instruction, even if you have some millions or billions lines of code, right? Because compiler has this liberty to take the entire view of the code, source code. On the other hand, if you just take a look at the hardware can definitely have the access to the present, that is some instructions which are being executed currently. But if you have some kind of profiling mechanisms involved in your hardware, then definitely it can also have the access to the past. But for future, the answer is no. I'm very sorry, hardware can't predict or can't anticipate the future. So the solution remains here. So compiler can actually anticipate the future instructions, and in this particular, by considering this particular property, compiler can actually instruct or can inform the hardware that these are the probable instructions which you are going to see next. So you can actually organize yourself or remaster yourself in some certain way so that you can maintain higher thermal efficiency as well as performance. In our research, so we have actually several application domains from where I usually consider several applications or benchmarks, like from approximate real-time computing, graphs, linear algebra, multimedia, neural networks, LLMs, and many more. Let's take a look at the TIMO. So this work was in collaboration with the IIT Mandi in India, and at that time I was working as a postdoc fellow at NTNU in Norway. So relaxed histogram is basically a kind of an histogram where you can actually change the retention time of the underlying circuitry. Okay, so conventional SRAM caches are usually suffering from low density. They have actually higher scalability. They have the scalability and high static power consumption. To ameliorate this problem, so MRAM or spin transfer torque RAM or STDRAM as a non-volatile memory has come into picture. By offering high endurance while comparing with the other NVMs, and also they have the lower leakage power, and they are also comparable read latency with the SRAM. But they are suffering from high write cost, as I mentioned earlier. So lower retention STDRAM can ameliorate the downsides of this of this higher write cost by reducing the write latency and energy as well, but that leads to premature expiry. So both upsides and downsides are really very crucial here to balance. So multi-retention cache is could be a solution. So where we have actually multiple retention zones that lies on a single cache memory, and refresh and write backs are the two approaches as a solution for relaxed STD-RAM. Okay. So once on the verge of expiry of the retention time of a particular cache block, either you need to refresh that particular block so that your retention time counter will be set at that will be reset at that particular time. Or you can actually write back the data to the next level of memory, and in this case, particularly to the off-chip memory, which is really costly to maintain the functional correctness. But yes, if you don't have the dirty data and it's on the verge of the expiry, instead of writing it back, you can simply invalidate that particular point. But yes, write back can actually incur more or higher MPKI, that is misses per kilo instruction, which can actually aggravate the performance. On the other hand, refresh can actually on the other hand, if you're going to employ refresh, that can also increase the power as well as performance cost as well. Okay, so with refresh, block is first read and written back into the cache. That means you can have actually higher energy usage here. Okay, so this is the comparison table between higher and lower retention time. So on the left, you have the lower misses. Of course, if you have higher retention time, you don't need to worry or don't need to do the repeated number of times of refreshes as well as write back operations. On the other hand, the writes are really costly. While you are considering the lower retention time, you have the definitely efficient writes, while with comparison to a higher retention zone, but definitely you have the higher misses or the overheads. So multi-retention cache could be a solution. Let's see how TIMO works. So before delve inside the architecture of TIMO, we'll see how we have analyzed the multi-set retention STD-RAM. So the retention span of the cache block lies within a range of 0 to 100 milliseconds, and that we have found from our empirical analysis through some of our simulation infrastructures. And then higher value of the cache set percentage, which is close to 82% for the write accesses in the lower retention group, that is 0 to 10 milliseconds. And for a read access block, 40% of the cache set belong to the retention range of 0 to 10 milliseconds, which actually motivated us to dedicate a separate group for the cache set for the write access block. That is a write intensive block specifically. So we have actually bifurcated the entire cache into two different time zones. So one is called the higher retention time zone, another is called the lower retention time zone, because read is really compared. So read cost in both retention zones are really comparable. So we don't care much about the read, but yes, of course, with the write, because if you have write intensive block, it is always beneficial to write them in the lower retention zone. So this is the read access percentage. You can see from this graph. So the above summary report actually is supported by this empirical results here. Okay, so we performed these experiments on a set of 2 different benchmark suites, and 5 of each is shown here. One is from Parsec, and another 5 is from Ligra benchmark suite. So this is the relaxed STD-RAM. This is basically a summary of WAP, or write access percentage. So 35% of cache blocks are allocated by read miss, and 65% of the cache blocks are really allocated by the write miss while we're using write allocate cache. And this kind of, if you see this kind of analysis, this will be a general tendency for us that to identify the all write intensive blocks which have arrived, which has arrived in the cache for some write miss. Okay, so the blocks which have actually arrived just because of some write miss will be treated as a write intensive block. But unfortunately, this is not a conclusive indication, because during execution we have seen that the write miss has brought some block in the cache, but that block has become read intensive after a while during execution. So on average, 35% of the cache writes are happening due to the black block allocated on the read miss, which is significantly high. So to combat this problem, that the which blocks are write intensive, which blocks are read intensive, we have actually proposed some idea in TIMO. So before delving inside the idea, we just have one more analysis, that is the thermal analysis. So what happens if you have the imbalanced write counts in different parts of the cache? The main problem is that this will, as the write cost is super high, that is there, especially the write energy is very high, that can generate some localized region with high temperature, which are known as actually hotspots on chip. So we have seen the spatial thermal difference between the difference between highest and lowest temperature across the entire cache region could be as high as 10 degrees Celsius, which is really significant, because situation further aggravates on the larger size cache, where you can see that the more than 14 or more than 10 degrees Celsius can also be seen here, which is even in some cases, which is very close to the 11 or 12 degrees Celsius. And these spatial thermal variance can impact the thermal stability, retention time, and the chip failure rate, because higher the temperature, it will actually reduce the chip lifetime. That is, the chip failure rate will also increase. Okay, so the bottommost graph actually shows that how temperature basically impacts the thermal stability. Okay, and this high spatial thermal variance causes the variable lifetime. That is, you have some imbalanced situation in the entire cache, which actually lead you to some kind of unpredictable or unfavorable performance of your for your applications. So this is the very first technique of the TIMO, which is called as ARBA, or Access Request Based Allocation. This idea got published in ASAP conference in 2021. So in this idea, so what we have done on the right-hand side, you have actually write set and read set that is shown in gray and blue. So this is the entire cache. So suppose we have 8 different cache set in a smaller, small prototype cache, and first 4 sets will be in the write set, which are actually implemented with the lower retention zone based cells, and the read set will be will be implemented with the higher retention zone cell. Now, from upper level cache, when there will be a request, the request will be sent to a particular controller that will actually guide you that if this is a read miss or write miss, you will actually guide it to some particular location in the cache, either of the retention zones. Okay, but while you are suppose you have some cache miss, you don't have the data in the cache, you are just fetching it from the lower level memory. Just if it is if this request is caused by a read miss, then definitely you are going to store the data in the read set while you are allocating them in the cache. Or if it is a write miss case, then you are going to store the data in the write set. Now, how to access them? So to access them with an efficient manner, because cache addressing plays the most vital role here, we added one small bit for each and every block that has some entry in the coherence directory. So in case of cache coherency, we maintain a directory, and this directory actually holds the metadata for the each and every blocks in the cache. And with that metadata, we're just adding one trace bit. That trace bit will basically guide us that where your next access should be when you are getting a request for a particular block. So either this block is located in the read set or in the write set, this trace bit will guide us. But there is a problem, because this in this particular case, in ARBA, we have a problem of we are actually storing some of the all the write miss based allocation in the write set and read miss based allocation in the read set. But if your data will become if your read intensive data becomes write intensive during execution, then it will be a problem. So it cannot handle that situation. So to cope up this situation, we have actually proposed the next idea called as ARBA Ready. Ready stands for redirection. So in case of redirection, what we have done is that you just see here that with the ARBA logic, we have added just one more circuitry called as write counter. This is basically a saturating write counter, where if the counter value in the read set for some block is more than a threshold, in this case, which is 3, and then you can actually redirect the write to that particular blocks from the next time. So, and this is basically monitored periodically. So the entire execution span is basically divided into even length of periods, and at the end of each period, you just try to figure out that what is the value of the write counter. If write counter is more higher than 3 or equals to 3 at least, then you can actually send the you can actually redirect the write to the write set of that particular block, and corresponding trace bit will be also changed there. Okay, now you are sending all write to the write set instead of writing it to the read. So first 2 or 3 writes will be allowed to the read set, but after that you can actually send it to the write. And in this particular case, we are not actually moving the block entirely from read set to write set, which is really a costly operation and could have some redundancy in terms of power usage. So what we have done, the very next write, when it will arrive to that particular read set, we'll just redirect the write to the write set, and we'll invariate the content of the read set for that particular block, which actually saves a significant amount of energy. But this architecture has some problem. Once again, the problem is that writes are mostly skewed, and they are actually their tendency is to make the write set more write intensive, and which is also a bit more costly operation, because your higher number of writes can actually increase the temperature of the write set, and their retention time will further drop in future. Okay, so to combat this problem, we then proposed ARBA balance. This is our next architecture, where everything remains same like the previous one, but except that a particular counter logic. So counter logic will not be there. Rather, what we are doing, we have attached some kind of concept called as fellow set. So one set from write set will become fellow or friend with another set of read set, and they can exchange the data among them. So and these two fellow sets will have the balanced number of write among them. Okay, so and this is done for every pair between the read set and write set. Sorry, means each and every pair of the read set and write set who are friend actually. Okay, and this is the threshold logic written on the bottom of the left, bottom left of the slide. And here you can see that how we can basically balance the writes among the read set and the write set, and we got some very good result. But there was a small issue here, that the write have still been skewed or still been balanced in this particular design, because if you balance write, then still the number of writes in the read set will have the higher energy usage if you write the same number of writes in the write set. Okay, so to combat this problem, we have actually added that particular counter that we have actually proposed a couple of slides back while talking about the ready. So this counter has been added with the previous logic of ARBA balance, and finally we have the architecture of the TIMO. So TIMO, in addition to that, TIMO also filters out the dead write block from the read set upon expiration of the retention period. Okay, so this is how basically TIMO works. And let's take a look at our floor plan and LLC layouts in our experimental setup. So this is our entire cache, entire chip area. So where you can have we have actually designed the core in this particular fashion, because this floor plan is really important in terms of generating the thermal traces. On the right hand side, we have the physical layout of the LLC at mat level. So mat is basically a small granular level of the cache, so which is in this case 16 KB of our 8 MB cache size. Okay, so with you can just imagine the entire cache is divided into smaller chunk, and where each and every chunk is called as mat. So and mat has the equal size across the entire cache. So there are three different layouts on the right hand side I have shown. So first A. So in case of A, we have actually the single. There are two clusters basically. First clusters, top clusters of the mats are basically the write sets, where the bottom cluster is basically the read set. So we have some kind of contiguous design, and then we have the B. We have actually alternative rows will be implemented with the read set and write set, or that is the higher and lower retention zones respectively. Then we have finally some checkerboard kind of pattern. But in case of non-volatile memories, we have actually studied that yes, this layout doesn't matter much, because they don't have very good lateral heat transfer among the mats. Okay, so lateral heat transfer is very very low in terms of non-volatile memories, unlike the MOSFET based designs. Okay, and you can see that this peak temperature, drop in peak temperature is almost similar for all these designs. Even they have for both read and write sets, and these outcomes are of course within also in line with the prior outcomes at the device level studies. So this is our result. So we have evaluated and evaluated our architecture called TIMO, and thermal analysis and reliability has been shown here. So thermal variance, you can see for these graphs are actually shown for the fluid element one application from a Parsec benchmark suite, and you have seen the thermal variance between read and write set with ARBA ready, and ARBA is 7.1 and 5.8 degrees Celsius respectively. With the right balance approach of ARBA balance, TIMO is also able to reduce the thermal variance by 5 degrees Celsius. On the bottom, we have the worst case retention failure probability. So here you can see the probability of the bit flip. That is one kind of error that happens just after once your retention time basically is over. So this probability is quite high in case of the STD-RAM baseline. So which is denoted as STD-RAM underscore B is really high on average, which is 0.34. And with TIMO, this failure has been reduced by 0.09, which is basically a 44% reduction for read set and 35% reduction for the write set. Now we have the thermal analysis and the reliability mode. So here you can see the percentage of reduction in terms of chip failure rate, so which is more than 95% for both TIMO read set and write set. And for the ratio of the thermal stability of read set and write set is very close to 1 for most of the cases here. Okay. So that implies that the TIMO really performs better than the prior work. And this is the major takeaways from TIMO, is that the spatial thermal variance in multi-retention STD-RAM cache that entails a non-uniform performance, and TIMO balances out the thermal variance to maintain a uniform power density. And ARBA ready and balance, they actually redirects the write intensive blocks and balances the write across the cache sets respectively. And finally, TIMO reduces the thermal variance from 8.1 to 4.2 degrees Celsius and reduces the failure rate by more than 95%, with an area overhead of 0.3%, which is really negligible. So this is how TIMO works. And next we have the hot ReRAM, so which is actually a simulation framework that we have prepared and got published in recent past. And this work was actually a big collaboration among these 6 different universities. And the prime challenge for the ReRAM or memory star-based cache memories was that they are facing thermal reliability issues, just like non-volatile memories like magnetic RAM. But we do not have any kind of simulation tools available at that time to model temperature effects alongside the performance and power. And as a solution, we have developed hot ReRAM, and this work took around 3.5 years to develop this kind of simulator, which is actually an open source one, and that provide actually fine-grained thermal analysis for the ReRAM caches while being integrated with some of the architectural tools like GEM5, non-volatile SIM, and hotspot. And the impact is it enables the detailed thermal profiling and optimization, quantifying significant temperature-induced performance variations, which is up to 14.5% for the reliable cache design. So this is basically a fine-grained thermal simulation model that, coupled with accurate modeling of temperature's impact on critical ReRAM parameters, offered with an open-source integrated framework. This is our proposed simulation model. This is the circuit level design of the ReRAM-based LLC. So this is a cell array. So in architectural level, this will be the layout of the LLC. Okay, the entire LLC is divided into 4 different banks. Let's say in this case, it's four banks, and the banks are divided into sub banks, and sub banks are divided into 4 mats here. So this is basically the mat level granularity which we have used in our thermal analysis for TIMO. And every mat is further divided into multiple sub-arrays, and each and every sub-array is basically the smallest unit here. And they have the precharger, row decoder, word line driver, column mark, sense amplifier, output driver, etc. as their I/O units. And also the cell array is the main part where you can actually store the data. And the configuration details are also given here. And in case of hot ReRAM simulation model, we have this is the entire structure of the simulation model. So PMC stands for performance monitoring counter, which are used, which we are basically collecting from GEM5, and especially we are following the LLC statistics. So LLC statistics involved, that is last level cache statistics like number of reads or number of writes at sub-array level or at mat level. And from there, we are sending the statistics periodically to NVSIM power model. But NVSIM power model is basically developed upon prior power model of the cache memory that doesn't have very good accuracy in terms of leakage computation, and it doesn't support the leakage computation for all kind of temperatures. So we developed our own leakage computation model and attached to the NVSIM power model. And this power model is basically verified by the VTIM simulation model, which was developed earlier, and we have actually implemented the entire circuit validation model for our simulator, where we have considered energy per bit, latency, and leakage, as well as the off resistance for different temperature values. And then these values will be actually sent to the thermal simulator called hot ReRAM. So hot ReRAM is basically we have attached up the entire ReRAM thermal model with the hotspot existing simulator, and that then simulate the steady state as well as transient temperature, whereas steady state will be next used for developing the thermal stability, retention time, and write latency of the underlying circuitry at mat level. So once you have this one, you can actually have the good study of the different parameters, like how thermal stability basically changes across the space and as well as across the time, because this will be the entire loop will run periodically. Okay, so for your entire execution. And of course, its computational cost could be high, but we have actually done some optimization to reduce the runtime cost of the entire simulation. But yes, it's almost similar with the GEM5 execution time at the moment. Can show you some sample simulation results. So this is the simulation result for the Black-Scholes taken from the Parsec benchmark switch, and read, write, allocate, and write back counts for match over 100 timestamps during an execution. So one timestamp basically here represents 1 million clock cycles at the frequency of 3 gigahertz. And then we have how temperature basically changes over time. So you have actually different power profile and temperature profiles here on the second graph. And the final one, we have the spatial thermal variance, that is the difference between the highest and lowest temperature in the cache. And you can see that this spatial thermal variance basically varies. It's between 3 and 8 degrees Celsius, 3 and 7 degrees Celsius, right? 3.5 to 7 degrees Celsius, which is quite high. And based upon that, we have considered the standard deviation in retention time for ReRAM-based LLC. And you can also see the maximum percentage increase in write latency for ReRAM LLC as well. In conclusion, I can say that thermal effects critically impact the ReRAM cache's reliability, yet comprehensive modeling tools were previously unavailable. Now we have the hot ReRAM, and which is one of the first open source simulation infrastructure that offers fine grain temperature aware thermal analysis for ReRAM based cache memories. And this quantifies the significant performance degradation up to 14.5% due to thermal variations, and highlighting the need for thermal management, which is really crucial in design at designing phase. And this tool enables the designers to analyze thermal properties, identify hotspots, and optimize ReRAM caches for enhanced reliability and performance. Finally, we have the last paper called TreeFET. I can give you a very brief about this one. So TreeFET is basically temperature over real-time task scheduling for FinFET-based multicores. And this work was also in collaboration with the IIIT Guwahati, where I used to work before joining NTNU as a postdoc fellow. And Ian Schul is my student, PhD student, so with whom still I'm working. And this is one of his, part of his PhD work. And this got published last year in ACM Text. And FinFET devices have basically improved computational computing capabilities of the hardware platform, but they also introduce thermal issues. As I mentioned, that these are the 3D devices, and so they have their conductive filament or the channel encapsulated by some thermal insulator. So heat is basically clogged within that particular channel, which is really really bad for the circuit health, because that can actually incur some kind of self-heating effects or shees. And whereas temperature effect inversion is the good property, so that is one of the upside at the high temperature, because at high temperature circuit delay drops, so your processor will work a bit more faster. And this TreeFET is a temperature over real-time scheduler that exploits TI to improve performance while mitigating SHEs. And TreeFET is basically the first real-time scheduling approach that accounts for TI and SHE phenomena of the FinFET-based multicore, along with an intense focus on runtime task characteristics. So this is the core concept. So we have basically two inputs, set of tasks and set of cores. And we need to basically map the set of tasks to the set of cores. Okay. So first, while your task will arrive at some particular point, you need to segregate the hot and cold task, whereas the cores will also be segregated by looking at their current temperature at the cold to hot cores. Okay. Cold and hot cores. Then once this sorting or segregation is done, then your scheduling algorithm or technique will basically partition the deadlines for individual tasks, and also find out some crucial task parameters which are really important for the final schedule. Then it actually tries to map by using some kind of heuristics, because this is very, very case specific study, and we're going to map some of the hot and cold tasks on the cold and hot cores respectively. And for each and every task to meet the deadline, we have actually assigned some kind of frequency. And this entire work will be done at the design phase, because pre-deployment or pre-runtime. Okay, once tasks have been deployed, so runtime thermal management will come into the picture during execution, and by that will actually obey some kind of constraints like assigned frequency as well as critical temperature, because your task should not work any frequency below the assigned one's magnitude. Okay, so you have actually maintained the assigned frequency that was assigned by some of your scheduling algorithm. And critical temperature is one of the crucial parameters that is really needs to be maintained, because once your circuit temperature goes above the critical temperature, there is a high chance that your chip will be damaged permanently. However, our contribution lies in three different points. So first one is that we have tried to maximize the TI exploitation while minimizing the self-heating effects, and we have also throttled the voltage or control the voltage during the memory stalls. That is when your processor will be basically experience a memory stall. It will stall for a while, and that stall will be used by reducing the voltage of the supply voltage of the processor, so that processor can actually save some amount of energy, or it can actually slow down once your request will come back from the memory. So your processor will be definitely turned on, or not turned on. Actually, its voltage will be increased so that it can actually reach to that specific frequency level. Then we have also done the opportunistic voltage spiking. This diagram will make it much more clearer. So A is basically the task allocation. So we have assigned actually 4 different tasks, T1 to T4, for 3 different frequency levels, where T1 and T2 will be executed at frequency 1, the lowest frequency level, and the T2 and T3 will be executed at F3 and F2 levels respectively. Now during runtime, you can see that how temperature will change. That is the dotted line, red dotted line in the figure B. But at the same time, you can see if this temperature changes, will also change the frequency, because we are using basically a FinFET based circuitry. So once your temperature will goes up, your frequency will also go up, right? So at high temperature, your frequency will be higher. So and that will actually reduce the entire span of the task execution. Okay, so task execution span has been reduced, but yes, you cannot allow your circuit to execute at some high temperature. So how can you actually cope up with this situation? So basically, the C is basically the task level DTM or dynamic thermal management at the core. So where you can see the red dot is basically the assigned frequency by your scheduling algorithm. During execution, the runtime frequency has go up. That is the dotted bold green line. That is average runtime frequency. And this discrete manner is basically it's basically saying that how you can actually control the frequency of, while executing the task. Now, come to the D. TI and SHA are frequency FGDVFS, that is fine-grained DVFS at memory stalls. So yellow part are basically the memory stalls, and during that memory stalls, you basically drop the voltage level. Once your voltage is dropped, you are going to save some energy, and that energy, that saved energy, could now be traded off to improve the performance by a small glitch or small spike in your voltage. So once your memory stall will be done, so your requested data has come back from the main memory, and your code needs to be operated at the assigned frequency level. That time you can actually spike your frequency some next higher level or at some turbo level just for a while, so that you have the saved energy, what you have saved during the stall, should not be violated. That is, once that span is over, and that is basically kind of calculated risk. Okay, so you should not violate the saved energy. So saved energy will be now traded off that for that particular glitch. And once that is done, you just come down by reducing the voltage at the assigned frequency level. So this is how it basically works. So you can see, if I just scale it, so you can see this diagram on the right side. So this is how the frequency and voltage things will work. Okay, so you're running at the frequency, that is the current frequency or assigned frequency, and F tar is basically the turbo frequency, and you're just increasing the voltage. At once your data will come back from the memory, you can just turn on the voltage, and then your frequency will also be increased. And after that, you just come down to the assigned frequency level. And by maintaining the DTM or dynamic thermal management, we can actually maintain the frequency at some particular level while our temperature is getting changed. Okay. So conventional systems usually experience a time gap between an LLC misdetection and dispatch stalls at the requester core. So core can actually be stalled for during any kind of off-chip memory access. So that is really common in modern systems, even in several kinds of out-of-order processor core as well. And the main idea is that the save energy during stalls and trade the saved energy once data is available at the cores. Okay. So this is the summary of this work. That is FinFET versus real-time systems. So FinFET introduces TI, but also SHEs, creating new challenges for real-time system designers. And FreeFET is a novel temperature-aware real-time scheduler designed to exploit TI while mitigating SHEs in FinFET-based multicores. And dynamic thermal management, or DTM, has been involved in FreeFET that uses a temperature cognizant or temperature-aware voltage frequency scaling mechanism to balance performance and temperature, ensuring deadlines are met while combating SHEs. And energy efficiency, in terms of energy efficiency, it actually has some 24% improvement in energy delay product by incorporating opportunistic voltage spiking to boost performance and enable energy saving techniques. And now in conclusion, so high performance is of course an endless demand for over the decades and since when the computer was born. And then off-chip thermal management has become a critical design issue. So over the last few decades, right? So once we are going below 45 nanometer technology nodes in MOSFET, since then it has become really, really crucial to design your entire things thermal efficient. And that exacerbated over the recent past with smaller technology nodes. Yes, of course, and that improves the improving performance per watt or reducing EDP is a primary objective for all kind of designs nowadays. So my current focus is to improve the performance per watt for the different 3D FET-based designs like FinFET and GAFETs, and also for the both for the processors and also for the caches, and general purpose computing as well as for the accelerators or some other devices. And for non-volatile devices, we have the ReRAM, STRAM, etc. Those designs are for we are targeting several conventional and unconventional computing like in-memory computing or some other edge-based computing and so on. And compiler and architecture can actually do some kind of interplay to balance the situation here, because as I mentioned initially, that compiler can have the look for the entire code. Okay, so it can actually visit the entire code from the first to the last instructions, even if you have billions of instructions, what computer architecture can't do. because what architecture can see that is available during runtime. So compiler can somehow anticipate the future behavior of the hardware, and that can actually inform the computer architecture of the underlying hardware. And accordingly, hardware can behave, or it can actually take a look at the compiler's information, and can also, by considering the current situation of the hardware in terms of power, performance, or temperature, it can actually work. It can actually improve the efficiency of the underlying circuitry. And in application domain, so we are currently working on several time-critical applications in terms of approximate real-time systems or normal real-time computing, time-critical systems, etc., and multimedia and and heavy algebraic operations, LLM, etc. And where mostly the back end of this kind of applications are coming from the hypergraphs, PDE solvers, heavy multimedia, and so on. And we can have actually three kinds of different applications. Some applications could be executed on CPU, only on CPU. Some will be only on GPU. But yes, but yes, of course, we don't have any kind of good set of applications or some particular set of applications that can actually executed both on CPU and GPU together. And we don't have this kind of benchmarks available. So one of my students is currently working on developing this kind of benchmarking now. So that can and the primary objective is to study the shared cache behavior while we have this kind of data. So that is, we have some shared data between the CPU and GPU. Okay, so I'm going to stop now. So this is some of my selected set of publications. And if you would like to join for any kind of collaborations or any kind of talk, so you can please feel free to drop me an email any point of time. Thank you. If you have any questions, please proceed.